Hey everyone, welcome back. And this is the start of a new series where we are going through AP Calculus AB from the ground up, starting with limits and eventually building our way up to derivatives, integrals, and everything in between. If you've made it through algebra and pre-calc, you're ready for calculus, and this series is for you. No calculus background is needed because we will be starting completely from scratch. Before we get started with today's topic of limits, let's just talk about what AP Calculus is and why it's sort of important for the real world. Everything that you've done in math up to this point, algebra, geometry, pre-calc, it deals with a lot of things that are fixed or that change at a constant rate. The slope of a line, area of a rectangle, average speed over a trip. But a lot of the real world doesn't change at a constant rate. So let's say we have an algebra problem. It's a classic. You have to find out how fast a car traveled over a certain period of time from point A to point B. And you're probably familiar with this formula. Speed equals distance over time. And if you want to get from point A to point B, you plug that in, make a formula, and your graph will look pretty linear like this. But is that really how it works? Let's say we want to actually plot it and we're doing some real-time simulations and tracking speed by the second. So we start off on the highway going pretty fast. Then we slow down because there's traffic. And then there's a red light, so complete stop. And then fast again because traffic seems to have gone to break. That's how it actually works, and the simple formula doesn't even teach you that. A car can speed up and slow down. A population can grow faster in some years than others. And the problem is that our usual tools, like distance over time for speed, only tell us the average over an interval. They can't tell us what's happening exactly at every moment. So the question that breaks up algebra is, how fast is a car going at exactly one moment in time? So what is a limit? The core idea is, in plain language, a limit asks, as x is getting closer and closer to a value, what value does the function get closer and closer to? So notice what it's not going to be asking. It's not going to be asking what the function is equal to at a certain point. It's just asking what the certain trend or direction it seems to be going in. It's basically what it's approaching. That distinction is very small, but it's crucial for understanding limits, and it's exactly why limits are so useful. A function could be approaching a value, even at a point where it's undefined, or it does something completely different than what's expected. This is what the notation looks like. And it reads, the limit as x approaches c of f of x equals k. Now, let's have a quick example. Imagine a function that's pretty much a straight line. And this is about at y equals 2, okay? But for some reason, at x is equal to negative 1, we have a bit of a gap. So, what would the limit be here? Well, as x approaches negative 1, f of x, what does it seem to be doing? Well, obviously it's undefined here because there's kind of a gap, but in calculus, you actually have to look at what it's approaching. So, since it still seems to be approaching 2, that will be our answer. The whole idea is that a limit will be describing the trend and not the destination. How do we actually find these limits in practice? The first tool that we'll look at is graphs. So, when you're looking at a graph, you check the value of the function that approaches from the left side of a point, and then what it approaches from the right side. And these are called one-sided limits. When we're looking at the left side, we're going to write it just like a normal limit notation. But to specify that we're looking at it from the left, we're going to add a little negative sign on the top right of our number. And everything else remains quite similar. Now, can you guess what we do for the right side? we essentially do the same thing, except instead of a minus, we'll do a plus. Let's have some example graph, and it's a pretty smooth graph, just like a normal function. So let's say we want to find a point, and let's say, what is it doing when x is approaching 4.5? So limit x approaching 4.5, f of x is equal to, let's see. Let's look at it from the left first. So from the left, as you can see, it's kind of swooping down, and it seems to just be approaching 0. So pretty easy. And then let's also look at it from the right. As it's approaching from the right, you can still see that it's also approaching 0. So our final limit here, if we don't want to specify, the limit as x approaches 4.5 of f of x is 0. But let's say we have a separate example. We have this new graph, and it seems to be kind of a quadratic function. But as soon as our function reaches -1, there's a separate sort of linear function that starts, almost as if it's completely separate. Well, this is where one-sided limits actually come into play. So as limit x is approaching, let's say 1, from the left side. So from the left side, it's going kind of down, and it's going to -3. So that'll be our answer for the left side. But what about the right side? Because it seems to be doing something completely different. So from the right side, it seems to be going a bit lower than the left side, and it's going to be at about -5. So one thing you should notice is that these two do not equal each other. And because of that, if anyone asks you, what's the limit when x is approaching 1? The answer will be that it does not exist. In order for a limit to exist, both sides need to be approaching the same point, like this. And this is completely different, which is why it's do not exist. But say we have another example. And here, let's say there's an asymptote when x is equal to 0. So our function seems to be going this way and seems to be going this way. So you might think at first that as limit x is approaching 0 from the left, and as limit x is approaching 0 from the right, you may think that you just write infinity because it seems to be going really up. Well, if it's ever approaching infinity, that means the function is unbounded, which means it has no set limit, which is exactly why we'll also write do not exist, or it does not exist. You can't really specify when it's going to infinity because it's not really a defined number, which is why we just write does not exist. One more example we could do is, let's say that we have this function, it goes like this, and then all of a sudden it just does a bunch of that. And this is what we call oscillating. So when we have a squiggly wave that just gets tighter and faster as it nears a vertical line, and in this case it's going to be about x is equal to 1, it doesn't need to be exact, and just by visibly compressing and oscillating, label it does not exist as well. So graphically, we're really checking one thing. Does the function settle down to one specific height as you approach from both sides? So the second tool that you'll want to know is tables, and this is really useful for when you don't have a graph or when you want a more precise numerical estimate rather than just looking at it with your eyes. So the idea is that you pick x values that get closer and closer to c from both below and above, and then you calculate f of x for each one. So let's use a real example for this function, and this table represents the function f of x is equal to squared minus 9 in parentheses divided by x minus 3. And we want to find the limit for when x is approaching 3. So here's the thing, if you just try and plug in x equals 3 directly, you will get 9 minus 9 over 3 minus 3, which is 0 divided by 0, and that's how you get undefined. So instead of just plugging in 3 directly, we're going to plug in the values really close to 3 and watch how the trend goes. So we have this 2-column table. Both sides are clearly homing in on 6. And in this table, as we can see, where we have the 3, these values are extremely close to 3, and we're about as close as we can be and precise as we can be for what 3 might be. And from both sides, it seems to be homing in on the value of 6. For this one, when limit x is approaching 3, f of x is going to be 6. Now, let's take a look at a case where the table tells us that the limit does not exist. And we have this second graph, and this one represents the function f of x is equal to absolute value of x divided by x. And we want to take a look at the limit as x is approaching the value of 0. So let's take a look at what's happening here. We're homing in on 0 with the x values, right? With these negative numbers and positive numbers being about as close to 0 as we can be from both sides. But on the right side, we can see that if we graph, the negative numbers are all going just at -1. Meanwhile, the positive numbers are all at 1. Does this remind you of something? Remember, when we're trying to figure out a limit and the left and right sides do not match, it means that the function's limit at that point does not exist. If both sides are clearly homing in on the same number, we can estimate that as a limit. But if two sides are trending towards different numbers, just like we saw with the graphs, the limit does not exist at that point. The nice thing about tables is that they turn what does the graph look like into what the numbers are actually doing, and it feels more concrete, especially for functions that are tricky to sketch by hand. All of these concepts set up the foundation for everything else calculus sits on top of, almost every idea. Next video, we'll build on this by learning algebraic techniques for finding limits exactly, without needing to estimate them from a graph or even a table. After that, we'll use limits to define the derivative, which is really where calculus starts to open up. So, if you found this useful, please consider subscribing and like. And please stick around for the rest of the series if you want to pass AP Calculus AB this year.